accelerating, if we go all the way back here, would have, non-zero terms for these. Like I said, any reference frame moving at a constant velocity you can consider at rest. 5 meters per second is no different than 0 meters per second. So any non-inertial reference frame would have non-zero terms from here. So there would be this non-inertial term that appeared. It didn't matter how that coordinate system was accelerated. Right? In my case, I talked about rotational acceleration, right? One that's just going around the circle. It could be going linearly, right? You would still get these these terms be non-zero.
So am I allowed with my understanding that your presentation here was made for our fixed inertial coordinate system, which is connected to the Earth data center, and far away stars give out the direction of the coordinate system, and all the computations you did for this particular case. Yes. While in general relativity, of course, you don't care about such things.
Yes.
And as far as I can understand, maybe most of the forces there, they appear as fictitious, no? Except the collision of particles.
And what?
Because you change the coordinate system. Your coordinate system can be moved in any way.
Yeah.
And you differentiate, you will get plenty of extra terms like this, which have to be understood as some fictitious forces.
Exactly.
So in general relativity calculation, maybe most of the forces there are fictitious because they're a result of acceleration. Something which is not collision of matter.
Yeah, any force that is not due to an interaction between particles is fictitious.
What about the gravity?
Gravity is
I don't think it's force at all.
Yes, that's something different. That's one of the 4 fundamental forces that's not theorized by an exchange of particles. The 4 fundamental forces, interactions, are gravitational, strong, weak, and electromagnetic. Strong, weak, and electromagnetic are all described by quantum field theory, which postulates that the force is not some imaginary sort of thing that you can't really see. It's not like a magical sort of thing. It's actually the exchange of messenger particles. So it's a physical contact between 2 particles. One virtual messenger particle, or in some cases a real messenger particle, and then a particle that feels the force. So even in terms of the strong, weak, and electromagnetic forces, which seem to happen with no direct contact between particles, they're still theorized as actual contact between particles. So as far as those 2 forces are concerned, the only real forces are contact forces. But in terms of gravitational, Einstein postulated that it was due to the curve in space-time. So due to curvature that attracts objects. So
the gravity force is
not in terms of classical mechanics. There is a lot of issues surrounding gravity and its unification. Obviously, gravity and its unification with the other 3 forces. I don't know what current theoretical physicists are classifying it as. I gave my lecture from a classical standpoint. From a classical standpoint, it's a real force. You would have to ask somebody who's doing unification how they feel about gravity. Because they would say that it's different. Actually, to a unification theorist, they would say it's the same. We just don't know why yet. To someone who does general relativity, they would feel that gravity is distinct from the other 3 forces because it can't be described by quantum field theory. But to a unification theorist who's trying to say that all the forces started at some fundamental force, and they broke off somewhere during the evolution of the universe, they would say ultimately, down to its most basic properties, the gravitational force should be no different than the other 3 forces. So it depends on who you ask.
But you mentioned here only fictitious forces because you were doing the example
specifically for the Earth. Yeah. This is the classic example. This is what most people who take undergraduate and graduate classical mechanics, this is what they would learn. They would learn the Coriolis and centrifugal force. All right, thanks a lot.
Thank you.